Right now, you are being watched by 6 cosmic predators. They do not move like planets. They do not burn like stars. They are mechanisms of annihilation so extreme that physics itself begins to collapse near their surfaces. One fires beams of gamma radiation that could sterilize half the galaxy in seconds. Another spins with magnetic fields a quadrillion times stronger than Earth's, tearing atoms apart at the quantum level. A third wanders through the void as a gravitational abyss, invisible and unstoppable, consuming light itself. These are not theoretical dangers. They are real objects cataloged by astronomers, lurking in our cosmic neighborhood. Some are close enough that their death throes could reach Earth within our lifetimes. Others operate on scales so vast that their violence rewrites the laws of space-time across billions of light years. The universe is not empty. It is a minefield. Between the stars, ancient machines of destruction orbit in silence, waiting for gravitational triggers or quantum fluctuations to awaken them. When they activate, they do not discriminate. They do not warn, they simply erase. What you are about to hear is not science fiction. Every object, every measurement, every catastrophic mechanism has been confirmed by observatories across Earth and in orbit. Astronomers have calculated the blast radii. Physicists have modeled the death scenarios. The mathematics are clear. Space is hunting us. There is a star 60,000 light-years from Earth that could kill you right now if it wanted to. Not through radiation that takes years to arrive. Not through gravity that pulls slowly across space. It could kill you through magnetism. Pure, incomprehensible magnetic force that operates on scales so extreme that the laws of atomic physics simply surrender. This star is called SGR 1806-20. It is a magnetar, and it is the most magnetic object ever discovered in the universe. On December 27, 2004, SGR 1806-20 had what astronomers politely call a flare event. What actually happened was closer to a magnetic apocalypse. The magnetar's surface violently restructured itself in less than 1/10 of a second, releasing more energy than our sun produces in 100,000 years. This explosion of magnetic energy raced outward at the speed of light, crossing 60,000 light-years of empty space before slamming into Earth's magnetosphere. The results were immediate and terrifying. Earth's ionosphere, the protective shell of charged particles that shields us from cosmic radiation, was instantly compressed by 30%. Communications satellites lost signal. Radio telescopes worldwide recorded readings so far off their scales that operators initially thought their instruments had malfunctioned. The Swift satellite, designed to detect gamma-ray bursts from dying stars billions of light-years away, was completely overwhelmed and had to shut down to avoid permanent damage. This was not a direct hit. This was the shockwave, the splash damage from an event 60,000 light-years distant. If SGR 1806-20 had been located just 10 light-years from Earth, the same distance as some of our nearest stellar neighbors, the December 2004 flare would have delivered a radiation dose sufficient to cause immediate mass extinctions. The magnetar's blast would have stripped away significant portions of our ozone layer within hours. Anything on the planet's day side would have been exposed to lethal doses of X-rays and gamma radiation. The electromagnetic pulse would have destroyed every electronic device on the hemisphere facing the blast. 10 light-years. That is closer than the star Epsilon Eridani. Closer than Tau Ceti, well within what astronomers consider our local neighborhood. And here is what should keep you awake. We have discovered approximately 30 magnetars in the Milky Way galaxy so far. Statistical models suggest there are approximately 30 million of them scattered throughout our galaxy, most too distant or too dim to detect with current technology. Some of those 30 million are certainly closer than 10 light-years. We just have not found them yet. Magnetars form through one of the most violent processes in stellar evolution. When a massive star, typically 15 to 20 times more massive than our Sun, exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes in less than 1 second, compressing matter to densities that exceed the inside of atomic nuclei. Protons and electrons are crushed together, forming neutrons and releasing enormous quantities of neutrinos that blast outward through the collapsing stellar material. What remains is a neutron star, a sphere roughly 20 kilometers across but containing 1.4 times the mass of our Sun. The density is so extreme that a teaspoon of neutron star material would weigh 4 billion tons on Earth. Gravity at the surface exceeds Earth's by 200 billion times. Light passing near a neutron star is bent so severely by gravitational distortion that you could theoretically see the back of the star by looking at its front. But neutron stars are not the end of the story. They are the beginning of the MAGNETARS horror. During the core collapse that creates a neutron star, something catastrophic happens to the magnetic field. Every star possesses a magnetic field generated by moving charged particles in its interior. When a star collapses from a sphere 15 times the width of our Sun down to an object 20 kilometers across, its magnetic field does not disappear. It concentrates. The magnetic field lines get compressed into an incomprehensibly small volume, amplifying their strength by factors of trillions. The result is a magnetic field so powerful that it defies comprehension. A typical magnetar possesses a surface magnetic field strength between 10 to the power of 14 and 10 to the power of 15 Gauss. For reference, Earth's magnetic field at the surface measures about 0.5 Gauss. A refrigerator magnet is about 100 Gauss. The strongest continuous magnetic field ever created in a laboratory reached approximately 45 Tesla or 450,000 Gauss and required enormous superconducting magnets and massive power supplies. A magnetar's field is 10 billion times stronger than anything humans have ever created, 20 trillion times stronger than Earth's protective magnetic cocoon. At these field strengths, magnetism stops being a simple attractive or repulsive force. It becomes a fundamental reshaping of reality itself. The quantum vacuum, the supposedly empty space between particles, becomes birefringent in the presence of such extreme magnetic fields. Light passing through this warped vacuum splits into separate polarizations and travels at slightly different speeds, an effect called vacuum birefringence that was purely theoretical until magnetars proved it actually happens in nature. Atoms themselves become elongated in strong magnetic fields, their electron clouds stretched into cigar shapes aligned with the field lines. At magnetar strength fields, this distortion becomes so extreme that atomic structure breaks down entirely. Hydrogen atoms, normally spherical clouds of probability where an electron orbits a proton, become long thin tubes hundreds of times longer than they are wide. Chemical bonds, which depend on electron orbital shapes, become impossible to form. Chemistry ceases to exist. The magnetic field near a magnetar is strong enough to be fatal from 1,000 kilometers away. At that distance, the field would disrupt the electrical signals in your nervous system, stopping your heart and brain function instantly. You would not feel pain. Your neurons simply would not be able to fire in the presence of such overwhelming magnetic force. Move closer to 100 kilometers, and the magnetic field begins affecting matter at the atomic level. The iron in your blood would attempt to align with the field lines. But this is not a gentle reorientation. The forces involved would rip iron atoms out of hemoglobin molecules. Your blood would separate into constituent elements. Your body would begin to dissociate at the molecular level. At 10 kilometers from a magnetar, you would be torn apart by magnetic forces stronger than the chemical bonds holding your atoms together. You would not explode outward like in a vacuum. You would stretch, elongated along magnetic field lines, pulled into a thin strand of ionized plasma that spirals down toward the star's surface. The magnetic field does not affect just matter. It warps space-time itself. Einstein's general relativity describes how mass and energy curve the fabric of space and time, creating what we experience as gravity. But magnetic fields also carry energy, and according to relativity, all energy contributes to space-time curvature. A magnetar's field contains so much energy that it creates measurable distortions in space-time separate from the neutron star's gravitational effects. Robert Duncan and Christopher Thompson, the astronomers who first proposed the existence of magnetars in 1992, calculated that the magnetic field of a magnetar contains enough energy to power our sun's entire luminous output for 100,000 years. This is not energy that can be tapped or harnessed. It is energy locked into the structure of magnetic field lines threading through and around a spinning ball of neutronium. That spin creates additional nightmares. Most magnetars rotate once every 2 to 12 seconds. This seems slow compared to pulsars, which can spin hundreds of times per second. But remember that we are talking about an object more massive than our sun, compressed to the size of a city, wrapped in the most powerful magnetic field in the universe. Every rotation drags those field lines through space, twisting them into complex geometries that store even more magnetic energy. The surface of a magnetar is a landscape that defies imagination. Neutronium, the degenerate matter that comprises the star, forms a solid crust approximately 1 kilometer thick. Beneath this crust lies a sea of superfluid neutrons, particles that flow without any friction or viscosity, obeying quantum mechanical rules that govern subatomic behavior. The crust is not smooth. Magnetic pressure buckles and warps the neutronium, creating mountains a few centimeters tall that contain more mass than Mount Everest. These mountains matter because they create imbalances. As the magnetar spins, its uneven mass distribution generates gravitational waves, literal ripples in spacetime, that propagate outward at light speed. The magnetar is continuously hemorrhaging energy through these gravitational waves, which causes it to spin down over time. The rotation slows by milliseconds per year. This spin down has catastrophic consequences. As the star rotates more slowly, the magnetic field lines that are anchored in the crust and extend through the interior into space become twisted and stressed. The field lines thread through the superfluid interior, through the solid crust, and out into the magnetosphere around the star, but different layers rotate at different rates due to the viscous coupling between them. Stress builds. The magnetic field lines become braided and kinked, storing ever-increasing amounts of energy like a rubber band being wound tighter and tighter. Eventually, something breaks. A starquake. The neutronium crust fractures suddenly, the surface of the star snapping like continental plates in an earthquake, but operating under forces 1 trillion times more powerful. The fracture propagates through the crust at speeds approaching 1/3 the speed of light. The crust shifts by micrometers, but those micrometers involve rearranging matter with the density of atomic nuclei. The sudden shift causes the magnetic field lines anchored in the crust to reconnect explosively. Magnetic energy that has been accumulating for years or decades is released in 1/10 of a second. This is what happened to SGR 1806-20 on December 27, 2004. The flare that struck Earth was a gamma-ray and X-ray burst containing approximately 10 to the power of 46 joules of energy. To put this in perspective, our sun releases approximately 3.8 times 10 to the power of 26 joules every second. The magnetar's flare released more energy in 1/10 of a second than our sun produces in 100,000 years. This energy was not released gradually. It erupted in a directional beam that swept across space like a cosmic lighthouse, and Earth happened to be in the path. The radiation hit Earth's magnetosphere traveling at light speed. There was no warning. The first photons arrived at the same instant that astronomers could theoretically have seen the flare begin. Earth's magnetic field, which normally protects us from solar wind and cosmic radiation, was overwhelmed. The ionosphere, located approximately 80 to 640 kilometers above Earth's surface, absorbed enormous quantities of high-energy photons. Electrons in the ionosphere were suddenly energized to far higher velocities than normal solar activity ever produces. This changed the ionosphere's electrical conductivity, disrupting the reflective properties that make long-distance radio communication possible. Ham radio operators worldwide reported complete signal loss. GPS satellites experienced temporary malfunctions as their signals were scattered by the disturbed ionosphere. The SWIFT satellite, launched just 3 months earlier, detected the flare and attempted to measure its intensity. The gamma-ray detectors were designed to observe distant events billions of light-years away, not a nearby magnetar flare. The instruments saturated immediately, recording off-scale readings for several minutes. SWIFT's flight computer, following pre-programmed safety protocols, shut down the gamma-ray detector to prevent permanent damage to the sensitive electronics. NASA's RXTE satellite, the Rossi X-ray Timing Explorer, also detected the flare. Its instruments were similarly overwhelmed. The high-energy X-ray timing experiment detector recorded flux levels 100 times higher than any previous event in its mission history. Scientists later calculated that the December 2004 flare was the brightest event ever recorded from beyond our solar system. And this was from 60,000 light-years away. Astronomers immediately began modeling what would happen if a magnetar flare of similar intensity occurred from a closer distance. The results were sobering. At 10 light-years, the radiation dose on Earth's surface would be lethal within hours for any organism lacking substantial shelter. The ozone layer would be partially or completely destroyed, allowing unfiltered ultraviolet radiation from our sun to reach the surface for years afterward. At 1 light-year, which is still far beyond any object currently threatening Earth, a magnetar flare would deliver enough radiation to cause global mass extinction. The planet's atmosphere would be ionized throughout, creating a glowing aurora visible even in daylight. Surface temperatures would spike as high-energy photons dumped their energy into the atmosphere. The electromagnetic pulse would destroy every electronic device on the hemisphere facing the flare, and induced currents and power lines would create surges that cascade through electrical grids worldwide. But the immediate radiation is only the first wave of destruction. Magnetar flares also accelerate particles to near-light speeds, creating cosmic rays that arrive hours to days after the initial photon burst. These cosmic rays are mostly protons and atomic nuclei that have been accelerated by the rapidly changing magnetic fields near the magnetar. When they strike Earth's atmosphere, they create cascades of secondary particles that penetrate deep into the atmosphere and potentially reach the surface. The cosmic ray bombardment would continue for weeks or months, depending on the magnetic geometry of interstellar space between the magnetar and Earth. This extended radiation exposure would increase mutation rates in all organisms, cause widespread radiation sickness in large animals, and potentially contaminate the food chain with radioactive isotopes created when cosmic rays strike atmospheric nitrogen and oxygen. There is no defense. Magnetar flares travel at light speed, meaning they arrive at the same moment we could theoretically see them coming. There is no time to evacuate, no way to shield an entire planet's population. The flare would strike, and we would have to survive with whatever protection we had in that instant. The geographic lottery would be brutal. If the flare struck during daylight hours on one hemisphere, that half of the planet would receive the full radiation dose, while the other hemisphere would be partially shielded by Earth's mass. But rotation ensures that no part of the planet could hide indefinitely, and atmospheric circulation would distribute radioactive isotopes globally within weeks. We have been extraordinarily fortunate. The nearest known magnetar to Earth is SGRO 418. -5,729, located approximately 6,000 light-years away. This is too distant to pose an immediate threat even if it produces a maximum intensity flare. The next closest, 1E1048 to 5,937, sits at approximately 9,000 light-years. But those are only the magnetars we have detected. They are identified primarily through their X-ray emissions, which means they must be relatively young and active to appear in surveys. Older magnetars cool over time, their surface temperatures dropping from millions of degrees to merely hundreds of thousands of degrees. These older objects become much fainter in X-rays and are easily missed in surveys. Statistical modeling suggests that for every active magnetar we detect, there are dozens or hundreds of inactive or quiet magnetars that remain invisible to current instruments. These sleeping giants could be much closer to Earth, invisible until they suddenly awaken with a starquake that generates a massive flare. The galaxy contains approximately 400 billion stars. If even 0.001% of them end their lives as magnetars, that implies 4 million magnetars scattered throughout the Milky Way. Most would be ancient and cold, their magnetic fields slowly decaying over millions of years. But decay is not linear. A magnetar can remain quiet for centuries and then suddenly produce a massive flare as crustal stress reaches a breaking point. Astronomical surveys are actively searching for these hidden objects. The Chandra X-ray Observatory, launched in 1999, has cataloged numerous X-ray sources that may be magnetars. The SWIFT satellite continues monitoring the sky for sudden X-ray bursts that could indicate magnetar flares. The upcoming IXPE mission, the Imaging X-ray Polarimetry Explorer, will measure X-ray polarization to study the extreme magnetic fields around neutron stars and magnetars. Every new detection adds data to our models, refining our understanding of how common these objects are and how frequently they flare. The statistics are not comforting. Magnetar flares appear to follow a power law distribution, meaning small flares are common and large flares are rare but not impossible. The December 2004 event from SGR 1806-20 was the largest ever recorded, but nothing in the physics prevents even more powerful events. The theoretical maximum for a magnetar flare remains poorly constrained. If an entire hemisphere of a magnetar's crust fractured simultaneously, releasing all the stored magnetic energy in one catastrophic reconnection event, the resulting burst could be orders of magnitude more powerful than anything observed. Such an event, called a hypergiant flare, is hypothetical but not forbidden by known physics. A hypergiant flare at 10 light-years would not just threaten life on Earth, it would threaten Earth itself. The radiation flux would be sufficient to blast away portions of the atmosphere. The planet's surface would be sterilized. The oceans would be heated, potentially triggering runaway greenhouse effects. Earth would survive as a physical object, but its biosphere would be obliterated. This is the magnetar's true horror. Not that it might kill us, but that it could erase all evidence we ever existed. In cosmic timescales, magnetars are temporary. They cool and fade over 10,000 to 1 million years, eventually becoming inert neutron stars with strong but no longer catastrophic magnetic fields. But during their active lives, they are random number generators of apocalypse, capable of sterilizing everything within a 10 light-year radius at unpredictable intervals. We orbit through space completely unaware of whether such an object lurks nearby, waiting for the next crustal fracture to send annihilation racing toward us at 300 million meters per second. The sky offers no warning. Magnetars are too small and too dim to see with optical telescopes. We detect them only after they flare. By then, the light that reveals them is the same light that delivers their payload. There is no gap between detection and arrival. The message is the weapon. There is an object in the constellation Lyra that could erase you from existence without ever knowing you were there. It is not a star. It is not a planet. It is a beam. A coherent stream of gamma radiation so energetic that a single photon carries more power than 1 trillion photons from our Sun. This beam is currently pointed away from Earth, sweeping through empty space like a lighthouse rotating in the cosmic dark. If it ever rotates toward us, we will have exactly 0 seconds to prepare. This is GRBO 80916C. It is a gamma-ray burst, and it is the most violent electromagnetic event ever recorded in the universe. On September 16, 2008, at 13 hours 13 minutes Universal Time, NASA's Fermi Gamma Ray Space Telescope detected something that should not exist. A pulse of gamma radiation so bright that it momentarily outshone every other gamma-ray source in the sky combined. The burst lasted 23 minutes, but the damage was done in the first millisecond. The source was 12.2 billion light-years away. The light had traveled for 12.2 billion years before reaching Earth, meaning we were observing an event that occurred when the universe was less than 600 million years old. At that distance, the gamma-ray burst was still bright enough to be seen by Earth-based telescopes. Astronomers calculated the total energy released. The number is incomprehensible. GRBO 80916C released approximately 8.8 times 10 to the power of 54 joules of energy. This is 500 times more energy than our Sun will produce during its entire 10 billion-year lifetime. This energy was released in 23 minutes. But even that number understates the horror, because gamma-ray bursts are not spherical explosions. They are beamed. The energy is concentrated into 2 narrow jets, each perhaps 5 to 10 degrees wide, that blast outward from the poles of a collapsing star at 99.9% the speed of light. This means the energy we measured from GRBO809116C was only the portion of the beam that happened to point toward Earth. The total energy released by the event, accounting for the fact that most of it sprayed into space in directions we could not observe, exceeds one solar mass worth of energy. Einstein's equation, E equals mc squared, tells us that mass and energy are equivalent. This gamma-ray burst converted more than the entire mass of our Sun into pure gamma radiation in less than half an hour. Nothing else in the universe produces this much energy this quickly. Not quasars, which take thousands of years to consume similar amounts of matter. Not supernovae, which release their energy over weeks. Gamma-ray bursts are peak power generators, and their peak is concentrated into beams narrow enough to sterilize the galaxy. The mechanism is called a collapsar. When a massive star, typically more than 30 times the mass of our Sun, exhausts its nuclear fuel, it collapses inward. But unlike the collapse that creates magnetars, which leaves behind a neutron star, the collapsar does not stop at neutronium density. The core is too massive. Gravitational pressure overwhelms even the degeneracy pressure that holds neutrons apart. The core becomes a black hole. This happens in less than 1 second. The outer layers of the star, still rich with hydrogen and helium from the star's atmosphere, are falling inward at speeds approaching 10% light speed. But the core has already collapsed into a black hole, and black holes have event horizons. Matter that crosses the event horizon is lost to the universe forever, unable to support the infalling material above it. The result is catastrophic. The infalling stellar envelope crashes into itself, creating a shockwave that rebounds outward. But not all the material escapes. Most of it continues falling toward the black hole, forming an accretion disk of superheated plasma that swirls around the event horizon at relativistic speeds. The black hole is spinning. It inherited angular momentum from the collapsing core, and conservation of angular momentum means the black hole spins at tremendous rates, potentially rotating hundreds of times per second. This spin drags space-time around it, creating a region called the ergosphere, where nothing can remain stationary. Magnetic field lines threading through the accretion disk get twisted and amplified by this rotating space-time. The magnetic fields become so strong that they extract rotational energy from the black hole itself, a process called the Blandford-Znajek mechanism. This energy is channeled along the rotation axis of the black hole, where the magnetic pressure is highest. The energy accelerates particles to velocities so close to light speed that relativistic effects dominate. These particles slam into the stellar material still falling inward, heating it to billions of degrees. The gas along the rotational poles becomes so hot and so energized that it punches through the collapsing star. Twin jets of plasma and gamma radiation bore through thousands of kilometers of stellar material in seconds, emerging from the star's surface at 99.95% the speed of light. These are the gamma-ray burst jets. From the side, you would see a star suddenly develop two brilliant spikes of light at its poles, jets that extend for light years within hours. From along the jet axis, you would see nothing until the gamma rays arrived at light speed, at which point you would experience the highest energy photons nature can produce, slamming into every molecule in your body simultaneously. Gamma rays are electromagnetic radiation, like visible light or radio waves, but with wavelengths shorter than the nucleus of an atom. A single gamma-ray photon from a typical burst carries energies exceeding 1 million electron volts. For reference, visible light photons carry about 2 electron volts. A gamma-ray photon is 500,000 times more energetic than the light you use to see. When a gamma-ray photon strikes an atom, it does not simply excite an electron to a higher energy level like visible light does. It tears through the atom entirely, ionizing it by physically ripping electrons away from the nucleus. The photon continues through matter, creating cascades of secondary particles as it interacts with atomic nuclei. A single gamma ray can ionize thousands of atoms before its energy is finally absorbed. Now imagine not one gamma ray, but 10 to the power of 55 of them, all arriving within seconds, all carrying millions of electron volts each. This is what happens when a gamma ray burst strikes a planet. In 1997, astronomers proposed that gamma-ray bursts might be responsible for past mass extinctions on Earth. The Ordovician extinction, which occurred 445 million years ago and killed approximately 85% of all marine species, shows evidence of being caused by sudden loss of ozone. Ozone forms in Earth's stratosphere when ultraviolet light from the sun splits oxygen molecules, allowing the free oxygen atoms to combine with other oxygen molecules to form O3. This ozone layer absorbs most of the sun's ultraviolet radiation, protecting the surface from wavelengths that damage DNA and other biological molecules. Without ozone, surface life is exposed to sterilizing levels of ultraviolet light. The Ordovician extinction shows signs of widespread ozone depletion that persisted for years, but no volcanic eruption or asteroid impact explains the pattern. Gamma-ray bursts offer a mechanism. When gamma rays strike the atmosphere, they ionize nitrogen and oxygen molecules. The free nitrogen and oxygen atoms quickly react to form nitrogen oxides, particularly nitrogen dioxide. These nitrogen oxides are extremely efficient at destroying ozone through catalytic reactions. A single nitrogen dioxide molecule can destroy thousands of ozone molecules before being removed from the atmosphere. The gamma rays from a burst would create so much nitrogen dioxide that the ozone layer would be depleted within weeks. The process would continue for years as nitrogen oxides slowly washed out of the atmosphere through rain and chemical reactions. Without ozone, the surface would be bathed in ultraviolet radiation from our sun. Photosynthesis in ocean plankton would shut down as UV radiation penetrated the upper layers of the ocean. These plankton form the base of the marine food chain, so their collapse would cascade upward, killing fish, then larger marine animals. On land, plants would suffer DNA damage, reducing agricultural productivity and disrupting terrestrial ecosystems. The fossil record shows exactly this pattern during the Ordovician extinction. Marine organisms were hit hardest, particularly those living in shallow water where UV radiation penetrates. Species that lived in deep water or had protective shells survived at higher rates. On land, spore-producing plants show evidence of increased DNA damage, consistent with elevated UV exposure. Astronomers calculated the required gamma-ray burst parameters to cause such an extinction. The burst would need to be within 6,000 light-years of Earth and aimed within 5 degrees of directly at our planet. The jet would need to have typical gamma-ray burst energies, around 10 to the power of 51 joules, focused into a narrow beam. Statistical models suggest this happens approximately once every 500 million years for any given planet in the galaxy. Earth has existed for 4.5 billion years. The Ordovician extinction occurred 445 million years ago. The timing fits. We may have been hit before. We will almost certainly be hit again. But the Ordovician scenario assumes a distant gamma-ray burst from the outer reaches of our galaxy. What happens if a gamma-ray burst occurs closer? At 1,000 light-years, a gamma-ray burst would deliver radiation doses exceeding lethal levels for any organism lacking substantial shelter. The atmosphere would heat rapidly as gamma rays deposited their energy into air molecules. The sky would glow with a brilliant blue-white light as the atmosphere ionized. Anyone looking upward would suffer immediate retinal damage from the intensity, even though gamma rays themselves are invisible. The initial pulse would last 10 to 100 seconds. During this time, the radiation dose at Earth's surface would accumulate to levels exceeding 10 sieverts, which causes death in 50% of exposed humans within weeks. But the immediate radiation is only the beginning. The gamma rays would create enormous quantities of nitrogen oxides in the atmosphere. Within hours, these chemicals would begin destroying ozone. Within weeks, the ozone layer would be reduced by 90% or more. The planet would be exposed to full solar ultraviolet radiation for years. Temperatures would spike. The ionized atmosphere would be a poor reflector of solar radiation, allowing more heat to reach the surface. Computer models suggest surface temperatures could increase by 10 to 20 degrees Celsius within months. The combination of increased heat and increased UV radiation would devastate ecosystems globally. At 100 light-years, the effects become apocalyptic. The gamma-ray burst would deliver instantaneous lethal radiation doses to the entire hemisphere facing the burst. Anyone outdoors would die within hours from acute radiation syndrome. The atmosphere itself would partially ionize, creating a glowing aurora visible even in daylight. The electromagnetic pulse from the gamma rays would be intense enough to induce currents in power lines and electronic devices. Electrical grids would fail, communication satellites would be destroyed, any electronics not in shielded enclosures would be permanently damaged. Modern civilization, dependent on electricity and communications, would collapse instantly on the affected hemisphere. But even this pales compared to what happens at 10 light-years or less. At 10 light-years, a gamma-ray burst does not simply threaten life, it threatens the atmosphere itself. The radiation flux would be sufficient to blast away portions of the atmosphere through a process called ablation. Gamma rays deposit so much energy into atmospheric molecules that they reach escape velocity and are literally blown off the planet. The process is called atmospheric stripping. It has been observed on planets orbiting close to active stars, where stellar flares heat the atmosphere enough to blow it into space. A gamma-ray burst at 10 light-years would deliver more energy in seconds than an active star produces in years. The atmospheric loss would be substantial, potentially reducing Earth's atmospheric pressure by 10% or more. The planet would be sterilized, no surface life would survive, the oceans would be heated, potentially boiling the upper layers, the climate system would collapse. Earth would require millions of years to recover, if recovery were even possible, without the biochemical processes that created our oxygen-rich atmosphere in the first place. And we would have no warning. Gamma-ray bursts are not preceded by any detectable signal. The jets travel at 99.9% the speed of light, which means they arrive only milliseconds after the photons that could have warned us. By the time we detect a gamma-ray burst, we are already being hit. Current gamma-ray burst detectors like Fermi and Swift can locate bursts to within a few degrees on the sky within seconds of detection. But this is not early warning. This is notification that we are already in the beam. The information arrives at the same time as the radiation. There is no defense. Earth's magnetic field, which protects us from solar wind and low-energy cosmic rays, is transparent to gamma rays. The atmosphere provides some shielding, but only for moderate energies. The gamma rays from a nearby burst would penetrate through the atmosphere, reaching the surface with minimal attenuation. Underground shelters would provide protection, but only if people could reach them within the 10 to 100 seconds of the initial pulse. Most of humanity would be exposed. The radiation dose would accumulate in seconds, far too fast for any evacuation. The aftermath would be worse than the initial blast. With the ozone layer destroyed and the electromagnetic infrastructure collapsed, survivors would face a planet with hostile surface conditions and no way to coordinate response efforts. Agriculture would fail under intense UV radiation. Supply chains would break down without communications. The population would crash. We have been monitoring the sky for gamma-ray bursts since the 1960s, when the Vela satellites, designed to detect nuclear weapons tests, accidentally discovered these cosmic explosions. In the decades since, astronomers have detected thousands of bursts. We now detect several per week from random locations across the sky. Most are billions of light-years away, too distant to pose any threat. But the galaxy contains hundreds of billions of stars, and a small fraction will end their lives as gamma-ray bursts. Statistical models suggest the Milky Way produces approximately 1 gamma-ray burst per million years. With the galaxy being roughly 100,000 light-years across, this means there is always a gamma-ray burst occurring somewhere in our galaxy approximately once every 10,000 years. Most of these bursts point away from Earth. The jets are narrow, only a few degrees wide, so the probability of being in the beam is low. But probability is not zero. Over geological timescales, Earth will eventually be hit by a galactic gamma-ray burst. Astronomers have identified several candidate stars that could produce gamma-ray bursts relatively soon in cosmic terms. Wolf-Rayet stars, massive stars that have already lost their hydrogen envelopes and are fusing heavy elements in their cores, are prime candidates. These stars are nearing the end of their lives and could collapse at any time. WR104, located approximately 8,000 light-years away in the constellation Sagittarius, is one such candidate. This Wolf-Rayet star is in a binary system, orbiting a companion star once every 240 days. The two stars are close enough that material from WR-104 flows toward the companion, creating a spiral pattern in the stellar wind. The geometry is concerning. WR-104's rotation axis appears to be oriented within 40 degrees of Earth. If WR-104 produces a gamma-ray burst when it collapses, and if the jet aligns with the rotation axis as theory predicts, Earth could be in or near the beam. At 8,000 light-years, WR-104 is too distant to cause immediate mass extinction, but it could still deplete the ozone layer and disrupt the climate. The burst would be visible in daylight, a second sun suddenly appearing in the sky for tens of seconds before fading. The gamma rays would arrive simultaneously with the visible light, giving no warning. Eta Carinae, one of the most massive stars known, is another candidate. Located approximately 7,500 light-years away, Eta Carinae is a blue hypergiant with a mass exceeding 100 times our Sun. The star is unstable, having undergone massive eruptions in the 1840s that briefly made it the second brightest star in the night sky. Eta Carinae will eventually collapse, potentially producing a gamma-ray burst. Its rotation axis is poorly constrained, so we cannot rule out being in the potential jet path. If Eta Carinae collapses while pointed at Earth, the effects would be similar to WR-104, but potentially more intense due to the star's extreme mass. These are the stars we know about. There are likely dozens or hundreds of similar objects in the galaxy that remain undiscovered because they are too distant or too obscured by interstellar dust. Any one of them could collapse tomorrow, and we would not know until the gamma rays arrived. The randomness is part of the horror. Gamma ray bursts do not target. They do not discriminate. They are not even aware that planets exist. They are simply the death screams of massive stars, converted into beams of annihilation that sweep through space at random orientations. If you happen to be in the way, you die. If you are not, you might never know the burst occurred. Astronomers search for these threats constantly. The SWIFT satellite was specifically designed to detect and locate gamma-ray bursts quickly, allowing ground-based telescopes to observe the afterglows before they fade. Fermi provides high-energy data that reveals the physical processes powering the bursts. Future missions like the proposed Theseus satellite will extend these observations to even higher energies and more distant bursts. But detection is not prevention. We cannot stop a gamma-ray burst. We cannot deflect one or shield against one. We can only watch as they occur throughout the universe, praying that none of them point at us. The universe produces gamma-ray bursts constantly. Somewhere in the observable cosmos, a star is collapsing right now, creating jets of gamma radiation that will travel through space for billions of years. Most will never hit anything. They will simply expand into the cosmic void, their energy gradually redshifting and diluting until they become indistinguishable from the background radiation. But some will hit planets, some will hit planets with life, and some will hit planets with civilizations advanced enough to understand what is happening to them in the seconds before they are sterilized. This is the gamma-ray burst's final cruelty. It operates at light speed, which means knowledge of the burst and death from the burst arrive simultaneously. There is no time between knowing and dying. The universe provides no grace period, no chance to say goodbye or take shelter. The message that you are about to die is delivered by the same photons that kill you. We scan the skies, we model the threats, we identify the candidate stars, and we wait, knowing that somewhere in the galaxy a star is collapsing, and we will not know if it is pointed at us until the day the sky turns blue-white and the radiation counters scream. There is something in your neighborhood that you cannot see, cannot hear, and cannot detect until you are already falling into it. It is not made of matter, it is made of absence, a hole in space-time so deep that not even light can climb out. It is smaller than a city, but more massive than the sun. And it is moving. Drifting through the galaxy at hundreds of kilometers per second, invisible against the cosmic dark, waiting for something to drift too close. This is a rogue black hole, and there are approximately 100 million of them wandering through the Milky Way right now. Black holes form when stars die, but not all black holes stay where they are born. When a massive star collapses into a black hole, the explosion is not always symmetric. If more material is ejected from one side than the other, the black hole receives a kick from the asymmetric supernova blast. This kick can reach velocities of 1,000 kilometers per second or more, enough to eject the newborn black hole from its birth cluster entirely. These kicked black holes become nomads. They drift through the galaxy, following trajectories that take them through spiral arms, across the galactic plane, and occasionally into the outskirts where stars are sparse and the darkness is nearly absolute. They do not emit light, they do not generate heat. They are simply regions of space-time so warped that nothing within the event horizon can ever escape. The event horizon is not a physical surface. It is a mathematical boundary, the point of no return where escape velocity equals the speed of light. For a stellar mass black hole of 10 solar masses, the event horizon has a radius of approximately 30 kilometers. This means the entire black hole, containing 10 times the mass of our Sun, is compressed into a sphere roughly the size of a large city. The density is incomprehensible. If you could somehow compress Earth to its Schwarzschild radius, the radius at which it would become a black hole, the resulting event horizon would be 9 millimeters across, a marble containing an entire planet. A stellar mass black hole takes this compression to extremes that challenge human understanding. Approaching a rogue black hole is not like approaching a star or planet. There is no glowing surface to warn you. There is no radiation to detect unless the black hole happens to be actively consuming matter. A lone black hole drifting through interstellar space is completely invisible. It reveals itself only through gravitational effects, and by the time those effects become noticeable, you are already in serious danger. Imagine a spacecraft traveling through what appears to be empty space. The stars ahead look normal. The stars behind look normal. There is no indication of any massive object nearby. The crew sees nothing unusual on their instruments. They are flying through a void. Then, gradually, they notice something strange. The stars ahead appear to be shifting position slightly, distorting as if viewed through rippled glass. This is gravitational lensing, the bending of light by space-time curvature. But the crew does not recognize the danger. They might assume it is an instrument malfunction or some exotic interstellar phenomenon. The distortion increases. Stars directly ahead begin to appear in duplicate. Multiple images formed as their light takes different paths around the massive object. The spacecraft's navigation system shows inconsistencies. The stars are not where they should be according to the ship's position and velocity. By now, it is too late. The spacecraft is within the gravitational influence of the black hole, experiencing tidal forces that begin to stress the hull. The difference in gravitational pull between the front and back of the ship creates tension. Metal groans, seams strain. If the crew attempts to thrust away from the unseen threat, they discover that their velocity has already been altered by the gravitational field. They are no longer traveling in a straight line. Their trajectory has curved, and depending on how close they approach the event horizon, they might already be on a collision course. The mathematics of escape are brutal. To escape from a given distance from a black hole requires achieving escape velocity at that distance. Near the event horizon, escape velocity approaches the speed of light. A spacecraft with chemical or even nuclear propulsion has no chance. The engines simply cannot generate sufficient thrust to overcome the gravitational pull. As the ship falls closer, tidal forces intensify. The force of gravity follows an inverse square law, becoming stronger as distance decreases. But this creates a problem for any extended object. The part of the object closer to the black hole experiences stronger gravity than the part farther away. This difference in gravitational force is called a tidal force, and near a black hole, it becomes lethal. For a 10 solar mass black hole, tidal forces become strong enough to tear apart a human body at a distance of approximately 600 kilometers from the event horizon. At this distance, the gravitational pull on your feet, assuming you are falling feet first, exceeds the pull on your head by thousands of newtons. Your body cannot withstand this stress. You would be stretched vertically and compressed horizontally, elongated into a thin stream of atoms. Physicists call this process spaghettification. It is not a metaphor. It is an accurate description of what happens to matter in strong tidal fields. Your body would literally become spaghetti-like, stretched into a long, thin strand as differential gravity pulls you apart at the molecular level. But you would not be conscious to experience this. The tidal forces on your body would disrupt blood flow to your brain within seconds. The difference in pressure between your head and feet would be so extreme that blood vessels would rupture. You would lose consciousness long before the tidal forces became strong enough to actually tear your body apart. The spacecraft would fare no better. The structural elements holding the ship together are designed to handle normal acceleration forces and atmospheric pressure differences. They are not designed to handle gravitational gradients of thousands of Gs per meter. The hull would crack. The ship would break apart into components, each component continuing to fall toward the event horizon independently. As you cross the event horizon, something strange happens from the perspective of an outside observer. You appear to slow down. Your image becomes red-shifted, shifting toward longer wavelengths as the light escaping from near the event horizon loses energy climbing out of the gravitational well. You become dimmer and redder, asymptotically approaching the event horizon but never quite reaching it from the outside perspective. This is gravitational time dilation. Time runs slower in strong gravitational fields, and at the event horizon, time dilation becomes infinite. From an outside perspective, you freeze at the event horizon, your image fading and red-shifting into invisibility over the course of hours or days. But from your perspective, nothing special happens at the event horizon. You cross it in finite time, still falling, still experiencing tidal forces. There is no barrier, no surface, no indication that you have passed the point of no return, except that the stars behind you become compressed into a shrinking circle while the darkness ahead expands to fill your vision. You are now inside the event horizon. The singularity lies ahead, inevitable. General relativity tells us that all future paths lead to the singularity. There is no direction you can point, no velocity you can achieve, that leads away from the center. The singularity is in your future as certainly as tomorrow is in your future in normal space-time. Time and space have exchanged roles inside the event horizon. Outside, you can move freely in space but must always move forward in time. Inside, you can move freely in time directions, but must always move inward in space. The singularity is not a place. It is a time. It is the moment when your world line terminates. What happens at the singularity remains unknown. General relativity predicts infinite curvature, infinite density, infinite tidal forces. The equations break down. The mathematical description of spacetime becomes meaningless. This is where physics fails, where our theories no longer provide predictions. Some theorists propose that quantum gravity effects become important at the singularity, preventing the formation of true infinities. Perhaps the singularity is not a point but a small region, where spacetime has Planck-scale structure, a foamy quantum geometry where our classical concepts of space and time dissolve. But we have no theory of quantum gravity, so these ideas remain speculative. What we know is that information cannot escape from inside the event horizon. Anything that falls in is lost to the outside universe. This includes information about the object's structure, composition, history, and quantum state. The black hole retains only three properties: mass, electric charge, and angular momentum. Everything else is erased. This creates a problem called the black hole information paradox. Quantum mechanics tells us that information cannot be destroyed. The quantum state of a system today determines its future state through unitary evolution, but black holes appear to destroy information, violating this principle. Stephen Hawking discovered in 1974 that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. Virtual particle pairs that constantly appear and disappear in empty space can be separated by the event horizon, with one particle falling in and the other escaping as real radiation. This Hawking radiation causes black holes to slowly evaporate. But Hawking radiation is thermal. It carries no information about what fell into the black hole. If black holes evaporate completely through Hawking radiation, the information that fell in appears to be permanently lost, violating quantum mechanics. The resolution to this paradox remains one of the biggest open questions in theoretical physics. Some proposals suggest that information is somehow encoded in the Hawking radiation in subtle correlations that become apparent only after the black hole has mostly evaporated. Others propose that information is preserved at the event horizon in a holographic encoding. Still, others suggest that black holes do not evaporate completely, but leave behind remnants that store the information. For our purposes, the implications are clear. Anything that falls into a black hole is effectively erased from the universe. If you fall in, you are gone. The matter making up your body will eventually be radiated away as Hawking radiation over timescales of 10 to the power of 67 years. But that radiation will bear no resemblance to you. The information that defined your structure, your memories, your quantum state is either lost or encoded in ways we cannot access. This is the existential horror of black holes. They are not just death, they are erasure. They remove things from existence so thoroughly that the universe itself forgets they ever were. And they are hunting. Not intentionally. Black holes do not have agency or purpose. But they move through the galaxy, and anything in their path is at risk. The typical velocity of stars in the galactic disk is approximately 220 kilometers per second. Rogue black holes move at similar velocities, sometimes faster if they received a strong kick at birth. They drift through interstellar space, occasionally passing through stellar systems. The probability of a rogue black hole passing through our solar system is extremely low. The galaxy is vast, and black holes are small. Space is mostly empty, even accounting for the 100 million rogue black holes that might exist in the Milky Way. But probability is not zero. If a stellar mass black hole passed within 1 astronomical unit of Earth, approximately the distance from Earth to the Sun, the gravitational perturbations would be catastrophic. Earth's orbit would be altered, potentially ejecting our planet from the solar system entirely, or throwing it into an elliptical orbit that makes it uninhabitable. The tidal forces would trigger earthquakes and volcanic eruptions as the black hole's gravity deforms Earth's crust. At closer distances, the tidal forces would tear the planet apart. The Roche limit, the distance at which tidal forces overcome a body's self-gravity, is approximately 18,000 kilometers for Earth orbiting a 10 solar mass black hole. At this distance, Earth would disintegrate, pulled into a ring of debris that spirals into the black hole over the course of hours. We would have some warning if a rogue black hole approached. The object's gravity would perturb the orbits of outer solar system objects like comets and Kuiper belt objects years before the black hole reached the inner system. Astronomers monitoring these objects would notice anomalies, but detecting a non-emitting black hole among the thousands of small objects in the outer solar system would be challenging. Gravitational wave detectors like LIGO and Virgo can detect black holes, but only when they are merging with other compact objects or spiraling into supermassive black holes. A lone black hole drifting through space does not generate detectable gravitational waves. It is silent. The only reliable detection method is gravitational microlensing. When a black hole passes between Earth and a distant star, the black hole's gravity bends light from the star, causing the star to briefly brighten and sometimes split into multiple images. Monitoring programs like OJLE and MOA search for these microlensing events, cataloging thousands per year. Most microlensing events are caused by ordinary stars or brown dwarfs, but some might be black holes. The difficulty is distinguishing black hole lensing from stellar lensing. The duration and shape of the light curve provide clues about the lensing object's mass, but the measurements are not always precise enough to distinguish a black hole from a very dim star. In 2011, astronomers detected a microlensing event designated MOA2-011-BLG191 OGLE 2011-BLG0462 that was consistent with a black hole of 3 to 10 solar masses passing through the line of sight. The event lasted several days, and detailed analysis suggested the lensing object emitted no light of its own. This might have been the first direct detection of a rogue black hole, or it might have been an unusually dim neutron star or white dwarf. The uncertainty remains. More recently, observations with the Hubble Space Telescope have attempted to detect isolated black holes through astrometric microlensing, where the black hole's gravity not only brightens the background star, but also shifts its apparent position slightly. In 2022, a team led by Kailash Sahu reported detecting a 7 solar mass black hole approximately 5,000 light-years away, moving through the galactic disk at approximately 45 kilometers per second. This black hole is not threatening Earth. It is too distant and moving in the wrong direction. But its discovery confirms that rogue black holes exist and can be detected. It also confirms that they are common. If we can detect one at 5,000 light-years despite the observational challenges, there must be many more too distant or poorly aligned to detect. The nearest known black hole to Earth is Gaia BH1, discovered in 2022 through analysis of data from the Gaia Space Telescope. This black hole is approximately 1,500 light-years away in a binary system with a Sun-like star. The black hole has a mass of approximately 10 solar masses and is not accreting material from its companion, making it extremely difficult to detect. It was found only through careful measurement of the companion star's orbital motion. Gaia BH1 is gravitationally bound to its companion star, so it is not a rogue. But its proximity suggests that closer stellar mass black holes might exist, perhaps within a few hundred light-years of Earth. These objects would be invisible to current surveys unless they happen to be in binary systems or cause detectable microlensing events. The galaxy's population of rogue black holes represents a diffuse threat. Each individual black hole is unlikely to pass near any given star system. But integrated over the galaxy's 400 billion stars and the billions of years of galactic history, encounters are inevitable. Some stellar systems have certainly been disrupted or destroyed by close encounters with rogue black holes. We do not see evidence of these events because they leave no permanent trace. A planetary system torn apart by a black hole becomes a debris field that dissipates over millions of years. The black hole continues on its journey, carrying no evidence of what it destroyed. There are no monuments to black hole victims, because black holes erase even the memory of their prey. The ultimate fate of rogue black holes depends on cosmic timescales. Over billions of years, gravitational interactions with stars and molecular clouds gradually slow the black holes down. Eventually, they settle into the galactic halo or fall toward the galactic center, where they might merge with the supermassive black hole at the Milky Way's core. For now, the rogue black holes continue their wandering, invisible hunters in the cosmic dark, waiting for the random chance that brings them into contact with matter. The night sky offers no warning. The stars shine steadily, revealing nothing of the darkness between them. We orbit through space completely unaware of whether a rogue black hole drifts nearby, its event horizon a sphere of perfect blackness against the already black background of space. Detection campaigns continue. Astronomers refine their microlensing observations, hoping to catalog the galaxy's rogue black hole population. But each detection requires precise alignment between Earth, the black hole, and a background star. The observations are difficult and time-consuming. Most rogue black holes will never be detected. They will drift through the galaxy for billions of years, interacting with nothing, visible to no one. They are the cosmic equivalent of ghosts, things that exist but cannot be seen, defined only by their effects on the space around them. This is the rogue black hole's final horror. It is not the violence of destruction or the pain of tidal forces, it is the erasure, the absolute deletion from the universe. If a rogue black hole consumed you, the universe would forget you existed. No information would remain, no trace, no echo. You would be gone as if you never were, deleted from reality by a wandering absence in space-time. There is a star moving so fast that it will escape the Milky Way entirely, and when it leaves, it will carry a planetary system with it into the intergalactic void. This is not speculation. This is observation. Astronomers have detected over 20 stars moving at velocities exceeding 500 kilometers per second, fast enough to overcome the gravitational pull of our entire galaxy. These objects are called hypervelocity stars, and they are the result of one of the most violent gravitational interactions known to physics. They are bullets fired from the galactic core, traveling at speeds that should not be possible for objects containing the mass of entire solar systems. And some of them are headed directly toward us. The first hypervelocity star was discovered in 2005 by Warren Brown and his team at the Harvard-Smithsonian Center for Astrophysics. The object, designated SDSS-J090745.0 plus 024507, is a blue star located approximately 200,000 light-years from the galactic center, well beyond the visible disk of the Milky Way. When Brown measured its velocity, the number made no sense. The star was moving at 709 kilometers per second relative to the galactic center. This is more than twice the escape velocity of the Milky Way at that distance. The star was not orbiting, it was leaving. Tracing its trajectory backward through space revealed that it originated from the galactic core approximately 80 million years ago. Something in the center of our galaxy had accelerated the star to escape velocity and ejected it like a bullet. The energy required is staggering. Moving a star that contains the mass of 3 suns to 700 kilometers per second requires approximately 10 to the power of 48 joules. This is more energy than our sun produces in 1 million years, delivered to a single object in a brief gravitational encounter. The mechanism is called the Hills mechanism, named after Jack Hills, who proposed it in 1988. The process requires a supermassive black hole, and fortunately or unfortunately, depending on your perspective, our galaxy has one. Sagittarius A star, the supermassive black hole at the Milky Way's core, contains approximately 4 million solar masses, compressed into a region smaller than Mercury's orbit. Binary star systems occasionally wander too close to Sagittarius A star. These binary systems are bound together by their mutual gravity, orbiting each other as they orbit the galactic center. But when they pass within a few light-years of the supermassive black hole, the black hole's tidal forces become stronger than the forces holding the binary together. The binary breaks apart. One star is captured by the black hole, spiraling inward to an eventual merger or close orbit. The other star is ejected. Conservation of energy demands this. The captured star loses orbital energy, falling toward the black hole. That lost energy must go somewhere. It goes into the escaping star, which is flung outward at tremendous velocity. The mathematics are brutal and precise. The closer the binary approaches the supermassive black hole before breaking apart, the more energy is available for the ejection. For a binary that penetrates to within 1 light-year of Sagittarius A star, the ejection velocities can reach 1,000 kilometers per second or more, fast enough to escape not just the Milky Way, but the entire local group of galaxies. These hypervelocity stars are time capsules from the galactic core. They carry information about conditions near Sagittarius A star millions of years ago, encoded in their compositions, velocities, and trajectories. By studying them, astronomers can probe the environment around the supermassive black hole without needing to observe the core directly through the intervening dust and gas that obscures our view. But they are also weapons. A star moving at 700 kilometers per second carries kinetic energy proportional to its mass times velocity squared. For a 3 solar mass star, this kinetic energy exceeds 10 to the power of 47 joules. This is roughly 100,000 times the energy that would be released if we converted Earth's entire mass into pure energy via Einstein's equation. If a hypervelocity star collided with another star, the results would be catastrophic. But space is vast and stars are small. Direct stellar collisions are extraordinarily rare. The greater danger comes from near misses. When a hypervelocity star passes within a few light-years of a normal stellar system, its gravitational influence perturbs the orbits of planets, comets, and asteroids. The degree of perturbation depends on the star's mass, velocity, and closest approach distance. For typical hypervelocity star parameters, passing within 1 light-year of our solar system would disrupt the orbits of objects in the Oort cloud, the distant reservoir of comets that surrounds our solar system at distances up to 100,000 astronomical units. These orbital disruptions would send comets plunging toward the inner solar system. Over the course of thousands to millions of years following the encounter, Earth would experience an elevated rate of comet impacts. Some of these comets would be large enough to cause mass extinction events if they struck the planet. The Chicxulub impact that killed the dinosaurs 66 million years ago released energy equivalent to 100 million megatons of TNT. This impact was caused by an asteroid or comet approximately 10 kilometers in diameter. A hypervelocity star flyby could send hundreds or thousands of similar objects toward the inner solar system over the following million years. But the immediate effects of the flyby would be worse. As the hypervelocity star approached, it would become visible as an extremely bright, fast-moving object in the sky. A 3-solar-mass blue star at 1 light-year distance would appear as bright as the full moon but blue-white instead of yellow. It would cast shadows. It would be visible during the daytime. This would cause panic, but the visual spectacle would be the least of our problems. The star's gravity would begin perturbing Earth's orbit. The gravitational influence of a 3-solar-mass object at 1 light-year is small compared to the Sun's gravity, but it is not negligible. Earth's orbital parameters would shift slightly, changing our distance from the Sun and potentially altering the planet's climate. The effects would be subtle at first. Average temperatures might change by a few degrees. Seasons would shift slightly. But these small changes accumulate over years and decades. Climate zones would migrate. Agricultural patterns would be disrupted. Coastal cities would face changing sea levels as polar ice responds to the temperature shifts. And this assumes a distant flyby at 1 light-year. If a hypervelocity star passed within 0.1 light-years, roughly 6,000 astronomical units, the gravitational perturbations would be far more severe. Earth's orbital eccentricity could increase, making our orbit more elliptical and creating extreme seasonal temperature variations. In the worst-case scenario, Earth could be ejected from the solar system entirely, becoming a rogue planet condemned to wander the galaxy in eternal darkness. The probability of such an encounter is low, but not zero. Approximately 20 confirmed hypervelocity stars have been detected so far, but these are only the brightest and most easily observed examples. Statistical models suggest the galaxy contains approximately 1,000 hypervelocity stars at any given time, most too dim or too distant to detect with current instruments. These stars are distributed throughout the galaxy, following ballistic trajectories that take them through the disk, into the halo, and eventually beyond the galaxy's visible boundaries. Most will never return. Once a star reaches escape velocity, it is gone forever, carrying any planetary systems it might host into the infinite dark between galaxies. Some hypervelocity stars have been observed to possess planets. The technique is difficult because the stars are distant and moving rapidly, making long-term observations challenging. But photometric monitoring has revealed hints of planetary transits around some hypervelocity candidates, suggesting that at least some of these stellar bullets retain their planetary retinues, despite the violent ejection from the galactic core. Imagine being on a planet orbiting a hypervelocity star. You would watch your home galaxy slowly shrink in the sky over millions of years as your star carries you away at 700 kilometers per second. The Milky Way would gradually transition from a band of light across the night sky to a spiral structure visible from outside, then to a dim patch of light, and eventually to just another galaxy among millions, indistinguishable from the rest. Your night sky would become progressively darker as your star escapes the galaxy's bright regions and enters the void between galaxies. Eventually, the only light would come from your own star and the most distant galaxies, dim smudges of light separated by billions of light years of absolute emptiness. You would be cosmically isolated. Any radio signals you transmitted would take millions of years to reach the nearest civilization, if any existed to receive them. You would be alone in the universe in a way that planetary civilizations within galaxies cannot comprehend. The void between galaxies is not just empty space. It is a different regime of existence, where matter is so sparse that atoms are separated by meters, where the temperature is just 3 degrees above absolute zero, where the only energy comes from the faint glow of the cosmic microwave background radiation. Some hypervelocity stars are moving even faster than the examples already discussed. In 2014, astronomers discovered US 708, a hypervelocity star moving at 1,200 kilometers per second. This is the fastest star ever observed escaping from the Milky Way. At this velocity, US 708 will reach the edge of the local group in approximately 30 million years. US 708 is particularly interesting because it is a white dwarf, the dense remnant of a dead star. White dwarfs are not normally ejected by the Hill's mechanism because they are too small and too dim to be part of the massive binary systems that interact with supermassive black holes. Instead, US 708 was likely ejected through a different mechanism involving a type Ia supernova. In this scenario, US 708 was part of a binary system where the companion star was transferring mass onto the white dwarf. White dwarfs have a maximum mass, called the Chandrasekhar limit, of approximately 1.4 solar masses. When a white dwarf exceeds this limit through mass transfer, it becomes unstable and explodes as a type Ia supernova. But the explosion is not symmetric. If the mass transfer has made the white dwarf rotate rapidly, the supernova explosion can be asymmetric, ejecting more material in some directions than others. The recoil from this asymmetric explosion can accelerate the surviving white dwarf to hypervelocity speeds. This is what appears to have happened to US 708. The discovery of US 708 revealed that hypervelocity objects are not limited to massive stars ejected from the galactic core. They can also be produced by supernova explosions in binary systems, which occur throughout the galaxy. This means hypervelocity objects might be more common than previously thought, and they might originate from anywhere in the Milky Way, not just the central region. Other exotic hypervelocity ejection mechanisms have been proposed. Some models suggest that interactions between multiple stars and a black hole can produce even higher velocities than simple binary disruption. Three-body or four-body interactions with a supermassive black hole can result in complex gravitational dynamics where one star is ejected at velocities exceeding 2,000 kilometers per second. At 2,000 kilometers per second, a star would cross the entire diameter of the Milky Way in 50 million years. It would escape the local group in 10 million years. These ultra-hypervelocity stars, if they exist, would be the fastest massive objects in the universe that are not relativistic particles. The fastest confirmed stellar object ever observed is S5 HVS1, discovered in 2019. This star is moving at approximately 1,750 kilometers per second. Having been ejected from the galactic center approximately 5 million years ago. Tracing its trajectory backward shows that it passed within approximately 0.04 light-years of Sagittarius A star, close enough for extreme tidal forces to operate. At this closest approach, S5 HVS1, or its binary companion, would have experienced gravitational acceleration exceeding 1 million Gs. For comparison, humans black out at approximately 9 Gs, and most structures fail at hundreds of Gs. The forces experienced by S5 HVS1 during its slingshot around the supermassive black hole were sufficient to distort the star itself, potentially triggering enhanced stellar activity or even structural changes in the star's interior. But S5 HVS1 survived. It is now racing away from the Milky Way at a velocity that will carry it into intergalactic space within 20 million years. When it leaves, it will be alone, the closest galaxy several million light-years distant, its light the only illumination in a void of absolute darkness. The detection of hypervelocity stars has improved dramatically with modern surveys. The Gaia Space Telescope, launched in 2013, has measured the positions and velocities of over 1 billion stars in the Milky Way. Within this dataset, astronomers are discovering hypervelocity candidates at an accelerating rate. As of 2023, over 50 strong candidates have been identified, with many more awaiting spectroscopic confirmation. This suggests that hypervelocity ejection is more common than early estimates predicted. The galactic center produces these stellar bullets at a rate of approximately 1 per 100,000 years. Over the galaxy's 10 billion-year lifetime, this means approximately 100,000 stars have been ejected at hypervelocity speeds. Most of these stars have long since left the galaxy, but the ones we observe now are in various stages of their escape. Some are still within the galactic disk, passing through stellar neighborhoods like ours on their way out. Others are in the halo, having cleared the main galactic structure but not yet reaching intergalactic space. The fastest have already left, invisible to our instruments, gone forever. Each hypervelocity star represents a binary system that was destroyed. For every star ejected, another star was captured by the supermassive black hole. Those captured stars spiral inward, their fates sealed. They will eventually cross the event horizon and be consumed, their mass adding to Sagittarius A star's already enormous bulk. The supermassive black hole grows through these captures, but slowly. A capture rate of 1 star per 100,000 years means Sagittarius A star is accreting approximately 1 solar mass per 100,000 years, or 10 to the power of -5 solar masses per year. This is negligible compared to the black hole's current mass of 4 million solar masses. But it accumulates. Over billions of years, these stellar captures will increase the black hole's mass by thousands or tens of thousands of solar masses. The black hole will grow, its event horizon will expand, and its tidal radius, the distance at which it can disrupt binary systems, will increase. This creates a positive feedback loop where a larger black hole can disrupt more distant binaries, leading to more captures and more growth. Eventually, in the far future, Sagittarius A star will be significantly more massive than it is today. Its influence will extend farther into the galaxy, disrupting stellar systems that are currently safe. The rate of hypervelocity ejections will increase. The galaxy will slowly bleed stars, losing mass to the intergalactic void one ejected star at a time. This process will continue for trillions of years until the galaxy has depleted its binary star population, or until the supermassive black hole has consumed or ejected so many stars that the galactic core becomes sparse. By that time, the universe will be radically different, its expansion having accelerated to the point where most galaxies beyond the local group have receded beyond the cosmic horizon. But for now, hypervelocity stars continue their journeys. They are scattered throughout the galaxy, some approaching us, some receding, all moving at speeds that defy intuition. Each one is a refugee from a destroyed binary system, carrying the scars of its violent ejection encoded in its chemical composition and velocity. When we detect these stars, we are observing the aftermath of gravitational violence that occurred millions of years ago near the supermassive black hole at our galaxy's core. We are seeing survivors, stars that escaped death by black hole consumption but were exiled from the galaxy forever. And we are seeing our possible future. If our solar system ever wanders too close to a massive black hole, whether through the slow migration of stars over billions of years or through a galactic merger that brings us near another galaxy's core, we could suffer the same fate. The sun could be captured and destroyed, or it could be ejected, carrying Earth and the other planets into the intergalactic void. Either outcome is extinction. Either outcome erases us from the galaxy. The only difference is the speed with which we die. Captured by a black hole, we would spiral inward over millions of years, watching the black hole grow larger in the sky as tidal forces gradually heat the Earth and boil the oceans. Ejected at hypervelocity, we would flee into the dark, watching the Milky Way shrink behind us as the sun becomes the only light in an increasingly empty sky. The hypervelocity stars we observe now are warnings. They show us that stellar systems are not permanent. Gravity can destroy them. Gravity can scatter them. Gravity can exile them to the cosmic void, where they will drift alone for trillions of years, isolated from every other star, forgotten by the galaxy that birthed them. This is the hypervelocity star's horror. Not death, but exile. Not destruction, but abandonment. These stars survive their ejection only to spend eternity alone, watching the universe expand until even the most distant galaxies fade from view, leaving nothing but darkness. There is a collision happening somewhere in the universe right now that is creating every atom of gold in your body. Not metaphorically, literally. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. Every atom heavier than iron in the entire universe was forged in the most violent collision physics allows. Two dead stars, each containing more mass than our sun, compressed into spheres 20 kilometers across, spiraling toward each other at a significant fraction of light speed, their surfaces already touching, already tearing each other apart. This is a kilonova, and when it detonates, it will produce more energy in 10 seconds than our sun will generate in 10 billion years. On August 17, 2017, at 12 hours 41 minutes Universal Time, every gravitational wave detector on Earth screamed simultaneously. LIGO's two detectors in Louisiana and Washington state registered a signal. Virgo in Italy confirmed it. The waveform was clear and unmistakable. Two neutron stars, each approximately 1.4 solar masses, had been orbiting each other for billions of years. Their orbit had been decaying through the emission of gravitational waves, causing them to spiral closer together. Now, they had reached the end. The merger took 3,000 orbits. Over the course of 100 seconds, the neutron stars circled each other 3,000 times, rotating faster and faster as they drew together. They were spinning around their common center of mass at approximately 1,000 times per second by the time their surfaces made contact. At that moment, matter that had been separated by 20 kilometers was suddenly occupying the same space. Neutronium, degenerate matter with the density of atomic nuclei, collided with itself at relativistic velocities. The impact released more energy in the first millisecond than the Sun produces in 100,000 years. But this was not an explosion. Not yet. The neutron stars were not destroyed by the initial contact. Instead, they merged, their surfaces flowing together like two drops of incompressible liquid. The collision created a temporary structure called a hypermassive neutron star, an object that exceeded the maximum mass that a static neutron star can support. A normal neutron star is held up against gravitational collapse by neutron degeneracy pressure. This is a quantum mechanical effect where neutrons resist being compressed into the same quantum state. It is the same effect that prevents electrons from being compressed in white dwarfs, but operating with neutrons instead of electrons. But neutron degeneracy pressure has limits. There is a maximum mass beyond which even neutrons cannot resist gravitational collapse. This limit, called the Tolman-Oppenheimer-Volkoff limit, is approximately 2 to 3 solar masses depending on the equation of state of ultra-dense matter. The exact value remains uncertain because we cannot replicate neutron star densities in laboratories. The merged object from the August 2017 event exceeded this limit immediately. It contained approximately 2.74 solar masses, well above the maximum for a static neutron star. But it did not collapse into a black hole instantly because it was rotating. The centrifugal force from rotation provided additional support against gravity. The hypermassive neutron star survived for approximately 100 milliseconds. During this time, it was the most extreme object in the universe. The density at its core exceeded 5 times 10 to the power of 17 kilograms per cubic meter. This is density beyond anything else known to exist, where the distinction between protons and neutrons begins to break down, and matter might transition into exotic states like quark matter. The surface was rotating at approximately 30% the speed of light. At these rotational velocities, the star was oblate, flattened into an ellipsoid by centrifugal force. The equator bulged outward while the poles remained relatively compressed. Matter at the equator experienced gravitational acceleration, partially cancelled by centrifugal acceleration, creating regions where escape velocity dropped below light speed despite being at the surface of a hypermassive object. This allowed mass ejection. Matter from the outer layers of the hypermassive neutron star was flung into space by a combination of tidal forces, centrifugal acceleration, and magnetic pressure. The ejected material consisted of neutron-rich nuclei, isotopes that do not exist naturally on Earth because they are too unstable. These neutron-rich nuclei immediately began undergoing nuclear reactions. Free neutrons were absorbed by heavy elements through a process called rapid neutron capture, or the R process. This is the only mechanism in nature capable of creating elements heavier than iron in significant quantities. Iron is special in nuclear physics. It has the most stable nucleus, the configuration with the lowest energy per nucleon. Creating elements lighter than iron through fusion releases energy, which is how stars power themselves. But creating elements heavier than iron through fusion requires energy input. Stars can create small amounts of elements slightly heavier than iron through slow neutron capture during their normal lifetimes, but they cannot create substantial quantities of the heaviest elements like gold, platinum, and uranium. For those, you need an R process. You need an environment with such a high density of free neutrons that atomic nuclei can capture dozens or hundreds of neutrons in seconds before they have time to undergo radioactive decay. The only known environment with these conditions is the ejected material from neutron-star mergers. In the August 2017 event, approximately 0.05 solar masses of material was ejected. This does not sound like much. It is only 5% of one solar mass, roughly 50 times the mass of Earth, but this material was composed almost entirely of heavy elements created through R process nucleosynthesis. The ejected material expanded at approximately 10 to 30% the speed of light. As it expanded, it cooled, and the neutron capture reactions ceased. But the newly created heavy elements were unstable. They began undergoing radioactive decay, releasing energy in the form of gamma rays, X-rays, and visible light. This is the kilonova, the optical and infrared transient produced by radioactive decay of our process elements. It is called a kilonova because it is approximately 1,000 times brighter than a classical nova, which is a thermonuclear explosion on the surface of a white dwarf. Telescopes worldwide turn toward the source within minutes of the gravitational wave detection. The SWOPE telescope in Chile was the first to detect the optical counterpart, 11 hours after the merger. It appeared as a bright point of light in the galaxy NGC 4993, located 130 million light-years from Earth in the constellation Hydra. Over the following days, the kilonova evolved. It brightened rapidly during the first day, reaching peak luminosity approximately 1 day after the merger. At peak, it was producing light at a rate of 5 times 10 to the power of 41 watts, approximately 10 billion times more luminous than our Sun. The spectrum was unlike any transient previously observed. It showed broad absorption features consistent with lanthanide elements, rare earth elements, with atomic numbers from 57 to 71. These elements are extraordinarily rare on Earth, making up only a few parts per million of the Earth's crust. But in the kilonova ejecta, they comprised significant fractions of the total mass. The color of the kilonova was also unusual. While most astronomical transients appear blue or white due to their high temperatures, the kilonova appeared distinctly red. This is because lanthanide elements have complex atomic structures with many electrons, creating dense force of absorption lines that block blue light while allowing red light to pass through. The kilonova's spectrum was dominated by lanthanide opacity, making it appear red despite temperatures exceeding 10,000 Kelvin. After peak brightness, the kilonova faded rapidly. Within 2 weeks, it had dimmed below the detection threshold of most telescopes. Within 1 month, only the most sensitive instruments could detect it. The ejected material continued expanding and cooling, eventually becoming transparent as the temperature dropped below the point where lanthanide opacity dominates. But the violence was not over. The hypermassive neutron star at the center of the merger had collapsed. After approximately 100 milliseconds of rotation-supported existence, it could no longer sustain itself. The rotation was slowing due to gravitational wave emission and magnetic braking. The centrifugal support weakened. Gravity won. The hypermassive neutron star collapsed into a black hole. This happened approximately 1.5 seconds after the initial merger, based on analysis of the gravitational wave signal and the timing of the gamma-ray burst that followed. The collapse was essentially instantaneous from an external reference frame. The entire 2.74 solar mass object disappeared inside its own event horizon in less than 1 millisecond. But black hole formation was not quiet. The collapsing neutron star was threaded with magnetic fields that had been amplified during the merger. As the star collapsed, these magnetic fields were compressed and twisted, storing enormous amounts of energy. The fields became so strong that they launched a jet of relativistic particles along the rotation axis. This jet punched through the surrounding ejecta and escaped into space, traveling at 99.95% the speed of light. When the jet material collided with the interstellar medium, it produced a gamma-ray burst, a pulse of high-energy photons that lasted approximately 2 seconds. The gamma-ray burst from the August 2017 event was detected by the Fermi Gamma-Ray Space Telescope 2 seconds after the gravitational waves, exactly the time delay expected for light to travel from the merger location to Earth. This was the first time a gravitational wave signal and an electromagnetic signal had been detected from the same event, confirming decades of theoretical predictions about neutron star mergers. The gamma-ray burst itself was relatively weak, at least by gamma-ray burst standards. It released approximately 10 to the power of 46 joules of gamma-ray energy, about 100,000 times less than the most powerful gamma-ray bursts observed from distant galaxies. This weakness was fortunate. If the gamma-ray burst had been pointed directly at Earth, the radiation dose would have been substantial. But the jet was not aimed at Earth. Careful analysis of the polarization and light curve evolution showed that we observed the merger from approximately 20 to 30 degrees off the jet axis. We saw the jet from the side, catching only the edge of the radiation cone. If we had been directly in the beam, the observed gamma-ray flux would have been 100 times higher. At 130 million light-years, even a direct hit from this gamma-ray burst would not have caused immediate harm. The radiation would have been absorbed by Earth's atmosphere, creating nitrogen oxides that would deplete ozone over the following months. The effects would have been similar to a distant gamma-ray burst, potentially increasing cancer rates and disrupting ecosystems, but not causing immediate mass extinction. But this was a weak gamma-ray burst from a distant source. What happens when kilonovae occur closer? The nearest neutron star binary system to Earth that will merge within the next billion years is located approximately 30,000 light-years away. This system, designated PSRJ 1946 plus 2052, contains two neutron stars orbiting each other with a merger time of approximately 500 million years. When these stars finally merge, they will produce a kilonova visible to the naked eye despite the distance. But 30,000 light-years is still safe. The gamma-ray burst produced by the merger will be attenuated by distance and interstellar absorption. Even a direct hit would not deliver lethal radiation doses at that range. The real danger comes from mergers within 1,000 light-years. At this distance, a kilonova's gamma-ray burst, if aimed at Earth, would deliver radiation equivalent to standing near a nuclear detonation. The atmosphere would provide some shielding, but gamma rays at these intensities penetrate deeply. Surface radiation levels would spike, the ozone layer would be devastated. The electromagnetic pulse would destroy unhardened electronics. The odds of such an event are low. Neutron star mergers are rare, occurring approximately once per 100,000 years in a typical galaxy like the Milky Way. The merger must also occur close enough to threaten Earth and must be oriented such that the gamma-ray burst jet points toward us. The jets are narrow, typically only 5 to 10 degrees wide, so the alignment probability is small. Combining these factors, the probability of Earth being struck by a dangerous kilonova gamma-ray burst is approximately once per 1 billion years. This is low enough that it is likely never happened during Earth's history as a life-bearing world, but high enough that it will eventually occur if the Earth and Sun survive long enough. But the gamma-ray burst is only one danger from kilonovae. The R-process material ejected during the merger is highly radioactive. It decays rapidly during the first days and weeks, powering the kilonova optical transient. But some isotopes have longer half-lives, remaining radioactive for thousands or millions of years. If Earth passed through the expanding debris cloud from a relatively nearby kilonova, these radioactive isotopes would be deposited in the atmosphere and on the surface. Elements like plutonium-244, with a half-life of 80 million years, would contaminate the environment. Thorium-232, with a half-life of 14 billion years, would persist essentially forever on human timescales. The radiation from these deposited isotopes would increase background radiation levels, elevating cancer rates and mutation rates in all organisms. The effect would be similar to the aftermath of a major nuclear disaster, but global and permanent. There would be no cleanup. The radioactive material would integrate into the biosphere, concentrating in food chains and accumulating in organisms. Evidence for past kilonova enrichment of Earth has been found in deep-sea sediments. In 1999, researchers discovered an excess of iron-60, a radioactive iron isotope with a half-life of 2.6 million years, in ocean floor samples dating to approximately 3 million years ago. iron-60 is not produced naturally on Earth. It must come from supernovae or kilonovae. The iron-60 spike suggests that Earth was dusted with supernova or kilonova ejecta approximately 3 million years ago. This source was likely several hundred light-years away, close enough to deposit measurable quantities of radioactive isotopes, but far enough to avoid immediate catastrophic effects. The biological impact remains uncertain, but the timing coincides roughly with some mammalian extinctions during the Pliocene epoch. The discovery raised disturbing questions. If one supernova or kilonova enriched Earth's environment with radioactive material 3 million years ago, others have likely occurred throughout Earth's history. Some might have been closer, depositing more material and causing more severe biological effects. The geological record of such events is fragmentary and easily erased by plate tectonics and erosion. Kilonovae also produce other hazards beyond gamma rays and radioactive fallout. The merger itself generates gravitational waves that propagate through space at light speed. These ripples in space-time are incredibly weak by the time they reach Earth. The August 2017 event distorted space by approximately 1 part in 10 to the power of 21 at Earth's location. This is a distance change of about 1,000th the diameter of a proton across the entire 4-kilometer length of LIGO's detector arms. But at close range, gravitational waves from neutron star mergers are not weak. Within 100,000 kilometers of the merger, gravitational wave amplitudes exceed 1 part in 10, meaning spacetime is stretching and compressing by 10%. Any object caught at this distance would be subjected to tidal forces that alternate at frequencies of 1,000 Hz, shaking the object violently at its resonant frequencies. A spacecraft at this distance would be torn apart by oscillating tidal forces. The hull would flex and crack. Internal components would vibrate destructively. Electronics would fail as circuit boards bent and broke. Any humans aboard would be killed by the vibrations alone, their internal organs liquefied by mechanical stress before the radiation arrived. Even farther away, at distances of 1 million kilometers, the gravitational waves would be strong enough to disrupt planetary orbits. A planet orbiting one member of the neutron star binary would be ejected during the merger, its orbital energy absorbed by gravitational wave emission during the final inspiral. The planet would be flung into space at velocities exceeding escape velocity, becoming a rogue planet condemned to wander the galaxy in darkness. The heat from KILONOVAE is also extreme. The radioactive decay that powers the optical display deposits approximately 10 to the power of 46 joules into the ejecta over the course of weeks. This energy heats the expanding material to tens of thousands of Kelvin, making it glow brightly in visible and infrared wavelengths. At close range, this thermal emission would be lethal. Within 1 light-year of a kilonova, the thermal flux during peak brightness would exceed the thermal flux from our Sun at Earth's orbit. Any planet at this distance would experience rapid heating. Atmospheres would expand, oceans would boil, the surface would become uninhabitable within hours. The expanding debris cloud itself presents hazards. Moving at 10 to 30% light speed, the ejecta would traverse 1 light-year in approximately 3 to 10 years. Any object in its path would be struck by neutron-rich nuclei traveling at relativistic velocities. The impacts would resemble cosmic ray hits, but at intensities millions of times higher than normal cosmic ray fluxes. A spacecraft caught in the expanding debris cloud would be sandblasted by relativistic particles. The hull would erode. Sensors would fail. Radiation levels inside the craft would spike as particles penetrated shielding. The crew would receive lethal radiation doses within minutes. For planetary systems, the effects depend on the planet's magnetic field and atmosphere. Earth's magnetic field deflects charged particles, providing some protection. But the intensities from kilonova ejecta would overwhelm the magnetosphere's defenses. Particles would penetrate to the upper atmosphere, creating auroras that span the entire sky and ionizing the atmosphere globally. The ionization would disrupt radio communications and damage satellites. The induced currents in power grids would create surges that could overwhelm protective systems. Modern technological civilization, dependent on electrical infrastructure and satellite communications, would face widespread failures lasting weeks or months as the debris cloud passed. KILONOVAE represent cosmic alchemy. They are the forges where the universe creates its heavy elements. Every atom of gold, platinum, uranium, thorium, and rare earth elements was created in a neutron star merger somewhere in the cosmos. These events are rare, occurring only once per 100,000 years per galaxy, but their products are scattered throughout space, enriching gas clouds that eventually form new stars and planets. Earth itself is made partially from kilonova ejecta, the heavy elements in our planet's core, the uranium that powers nuclear reactors, the gold in your jewelry, all originated in neutron star mergers that occurred billions of years ago in the molecular cloud that eventually collapsed to form our solar system. You are made of stardust, but specifically, you are made of kilonova dust. The heavy elements in your body were forged in the most violent collisions the universe produces. This means that every advanced technological civilization requires kilonova. Without neutron star mergers to produce heavy elements, planets would consist only of hydrogen, helium, and light elements up to iron. There would be no uranium for nuclear power, no rare earth elements for electronics, no heavy elements for complex chemistry. Technology as we know it would be impossible. We owe our existence to KILONOVAE, but we also live under their threat. The same process that created the elements necessary for life and technology produces radiation and debris that can sterilize worlds. We are products of cosmic violence, children of explosions powerful enough to outshine galaxies. And somewhere in the universe, right now, 2 neutron stars are completing their final orbits. They have been circling each other for billions of years, gradually spiraling closer through the emission of gravitational waves. Now they are minutes or seconds from merger. Their surfaces are beginning to deform, pulled into egg shapes by mutual tidal forces. The orbital velocity has reached a significant fraction of light speed. In moments they will touch, the collision will forge new heavy elements. It will generate gravitational waves that ripple across the universe. It will produce a gamma-ray burst that could sterilize any planet unfortunate enough to be in the beam. And it will create a kilonova, a brilliant transient that momentarily outshines its host galaxy, a cosmic beacon announcing that the universe is building the periodic table one violent collision at a time. This is happening now, and it will happen again and again. The universe does not stop forging elements simply because the process is deadly to any life nearby. Cosmic alchemy continues, indifferent to its collateral damage. The vacuum of space is not empty. It is seething with energy, and that energy might be unstable. Right now, at this moment, there could be a sphere of true vacuum expanding through the cosmos at the speed of light, erasing everything it touches. Not destroying it in the conventional sense, not breaking it apart or heating it or irradiating it, erasing it, rewriting the fundamental constants of physics so that matter as we know it cannot exist. This sphere could be 1 light-year away or 1 billion light-years away. It makes no difference. When it arrives, there will be no warning. The expanding bubble of true vacuum travels at light speed, which means the information that it exists arrives at the same instant as the bubble itself. By the time you could theoretically detect it, you would already be inside it. You would already be gone. This is vacuum decay. It is not an object in the traditional sense. It is a phase transition in the quantum fields that underlie all of reality. And it represents the only threat on this list that could destroy not just Earth, not just the solar system, not just the galaxy, but the entire universe simultaneously across all of space-time. The vacuum of space, the supposedly empty regions between particles, is not actually empty according to quantum field theory. It is filled with quantum fields that permeate all of space. The electromagnetic field exists everywhere. The electron field exists everywhere. The quark fields, the gluon fields, the Higgs field, all of them extend throughout the entire universe. These fields have ground states, minimum energy configurations where the fields are at their lowest possible energy. We call this ground state the vacuum. When we say space is empty, we mean these quantum fields are in their vacuum state, containing no particles but still possessing their minimum baseline energy. But here is the problem. What we call the vacuum state might not actually be the true ground state of the universe. It might be a false vacuum, a metastable state that appears stable but is actually sitting in a higher energy configuration than the true minimum. The universe might be trapped in a local minimum of energy rather than the absolute minimum. Think of a ball sitting in a small valley on the side of a mountain. The ball is stable. It will sit in that valley indefinitely unless something disturbs it. But the ball is not in the lowest possible energy state. The true ground state would be at the bottom of the mountain, far below. The valley is a false equilibrium. The ball is metastable. If something pushes the ball hard enough to get it over the rim of the valley, it will roll down the mountainside toward the true minimum. Once this process starts, it cannot be stopped. The ball will cascade downward, releasing all the potential energy stored in its elevated position. The descent is inevitable and irreversible. This is vacuum decay. If our universe exists in a false vacuum state, quantum tunneling could spontaneously create a bubble of true vacuum somewhere in space. Inside this bubble, the quantum fields would reconfigure to their true ground state, The bubble would then expand at the speed of light, converting false vacuum to true vacuum as it grows. The energy difference between the false vacuum and true vacuum would be released as the bubble expands. This energy release would be catastrophic. But worse than the energy release is the fact that the laws of physics inside the true vacuum bubble would be different. The fundamental constants that determine how particles interact would have different values. The masses of particles would change, the strengths of forces would change, chemistry would break down, atoms would dissolve. Matter would cease to exist in any form we recognize. The mathematics of vacuum decay were first explored by Sidney Coleman and Frank DeLucia in 1977. They calculated the probability that a bubble of true vacuum could spontaneously form through quantum tunneling. The answer depends on the energy difference between false vacuum and true vacuum and on the shape of the potential energy landscape that describes the quantum fields. For most reasonable parameters, the probability is extremely low. The expected time until vacuum decay occurs in any given region of space exceeds 10 to the power of 100 years, far longer than the current age of the universe. But probability is not zero, and the universe is large. With 10 to the power of 80 atoms in the observable universe and tens of billions of years of cosmic history, even extremely unlikely events become possible. If vacuum decay begins anywhere in the observable universe, the bubble expands at light speed in all directions. It is not limited by the expansion of space because it is not traveling through space. It is converting space itself from one configuration to another. The bubble's edge is a wall of destruction moving at 300,000 kilometers per second, and nothing can outrun it. When the bubble wall reaches Earth, the planet will not explode. It will not vaporize. It will simply cease to be. The atoms making up the Earth will find that they cannot exist under the new physical laws inside the true vacuum bubble. The electromagnetic force, which holds atoms together, might have a different strength. The masses of electrons and quarks might change. The configurations of particles that we call atoms would no longer be stable. Matter would decay into the lightest possible particles under the new physics. These particles might be completely different from anything in our current particle zoo. They might interact through forces we have no names for. The energy released by the dissolution of all matter would be enormous, but there would be nothing left to experience it. The Earth would be gone, converted into exotic radiation and particles that cannot form stable structures. You would not feel pain. You would not have time to think or react or comprehend what was happening. Your neurons require specific chemical reactions to fire, reactions that depend on electromagnetic forces having exactly the right strength to allow stable molecules. When those forces change, your brain stops functioning instantly. Consciousness requires a substrate that obeys the laws of physics we evolved under. Change those laws, and consciousness vanishes. The entire solar system would be converted in approximately 8 hours, the time it takes light to travel from the Sun to beyond Neptune's orbit. Mars would vanish 40 minutes after Earth, Jupiter an hour after that. The outer planets would follow in sequence, each disappearing the moment the bubble wall reached them. The Sun itself would dissolve, its nuclear fusion reactions ceasing as the strong nuclear force that binds protons and neutrons suddenly operates under different rules. The galaxy would take 100,000 years to be completely converted, the time required for light to cross from one side of the Milky Way to the other. But the process is inexorable. Every star, every planet, every atom in 400 billion star systems would be rewritten into exotic matter that cannot support the existence of life or structure or complexity. The observable universe, stretching 93 billion light-years across, would require 93 billion years to be fully converted. But this is irrelevant to us. Long before the bubble wall reaches the edge of the observable universe, everything we can see will have been erased. The cosmic microwave background radiation would be converted. Distant galaxies would wink out of existence as the bubble wall reaches them. Eventually, the entire universe would consist of nothing but true vacuum and whatever strange physics operates within it. This is not destruction. This is replacement. The universe does not end. It transforms into something else, something governed by different laws where our form of matter cannot exist. It might be a universe filled with exotic particles that interact in ways we cannot imagine. Or it might be empty, The true vacuum state, supporting no stable structures at all, just a featureless expanse of quantum fields in their absolute ground state. The probability of vacuum decay depends critically on the Higgs boson mass. The Higgs field is the quantum field responsible for giving particles their mass. Its properties determine whether our vacuum is stable, metastable, or unstable. When the Large Hadron Collider discovered the Higgs boson in 2012, physicists measured its mass at approximately 125 GeV. This measurement was troubling. Calculations show that with a Higgs mass of 125 GeV, the universe sits very close to the boundary between stability and metastability. Small changes in other parameters, like the top quark mass, can push the vacuum into the metastable regime where decay becomes possible. In 2013, a team led by Joseph Lekin and Maria Spyropoulou published calculations showing that based on current measurements, the universe is likely metastable. The vacuum we exist in is not the true ground state. It is a false vacuum that will eventually decay, though the timescale for this decay is incomprehensibly long under normal conditions. The expected lifetime of the false vacuum is approximately 10 to the power of 100 years. This is 10 to the power of 90 times longer than the current age of the universe. For all practical purposes, the vacuum is stable on any timescale relevant to human civilization or even the lifetime of stars. The universe will end through heat death, the gradual dissipation of all usable energy long before vacuum decay becomes probable. But this assumes normal conditions. High-energy processes can dramatically increase the probability of vacuum decay. If energy densities become high enough, they can push the quantum fields over the barrier separating false vacuum from true vacuum, nucleating a bubble of true vacuum immediately. The early universe might have been in such a high-energy state. In the first fractions of a second after the Big Bang, temperatures exceeded 10 to the power of 32 Kelvin. At these energies, the Higgs field would have been in a different configuration, and vacuum decay might have been much more probable. The fact that we exist suggests that either vacuum decay did not occur, or the early universe was actually in the true vacuum state and later transitioned to the current false vacuum through some unknown mechanism. Particle accelerators on Earth reach high energies, but nothing approaching the energies of the early universe. The Large Hadron Collider produces collisions at energies of 13 tera-electronvolts. Impressive by human standards, but 13 orders of magnitude below the Planck energy where quantum gravity effects dominate. These energies are not sufficient to nucleate vacuum decay. But cosmic rays reach far higher energies. The highest energy cosmic ray ever detected, the Oh My God particle observed in 1991, carried energy of approximately 3 times 10 to the power of 20 electron volts. This single particle, likely a proton, possessed kinetic energy equivalent to a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. If high-energy cosmic rays could trigger vacuum decay, the universe would have ended long ago. Cosmic rays at these extreme energies strike Earth's atmosphere approximately once per century. They have been striking planets and interstellar gas throughout the universe for billions of years. The fact that vacuum decay has not occurred suggests that either our vacuum is more stable than calculations indicate, or the energies required to trigger decay are even higher than the most energetic cosmic rays. Some physicists worry about artificial processes triggering vacuum decay. If particle accelerators continue to increase in energy, eventually reaching energies that approach or exceed the highest energy cosmic rays, could they accidentally nucleate a bubble of true vacuum? Could an experiment designed to probe the fundamental structure of reality inadvertently destroy the universe? The consensus among physicists is that this risk is negligible. If cosmic rays have not triggered vacuum decay, despite billions of years of bombardment at extreme energies, then human-made accelerators operating at lower energies pose no additional risk. The cosmic ray argument provides a form of safety assurance. Nature has already performed the experiment millions or billions of times without destroying the universe. But the cosmic ray argument has limits. It assumes that vacuum decay risk depends only on the energy of individual particles. Some scenarios involve more complex triggering mechanisms that might depend on collision geometry, interaction rates, or the production of specific particle species that cosmic ray collisions do not generate efficiently. The risk is almost certainly zero. But almost certainly is not absolutely certainly. The consequences of being wrong are infinite. If an accelerator experiment triggered vacuum decay, the bubble of true vacuum would expand from the collision point at light speed. CERN, located on the border between Switzerland and France, would be converted instantly. The bubble would reach the Atlantic Ocean in approximately 0.02 seconds. It would engulf Earth entirely in 0.04 seconds. Within 8.5 minutes, the bubble would reach the Sun. Within 5.5 hours, it would pass Pluto. The solar system would be gone, and the bubble would continue expanding forever, eventually converting the entire observable universe. There would be no survivors, no escape, no warning. The only entities that might persist would be outside the observable universe, regions so distant that light from them has not yet had time to reach us. But even these regions would eventually be converted, as the bubble continues its expansion for eternity. This is the vacuum decay's ultimate horror. It is not local. It is not temporary. It is permanent and universal. Once begun, vacuum decay cannot be stopped or reversed. The bubble does not slow down or dissipate. It expands at light speed forever, rewriting the laws of physics throughout all of space, until nothing remains that resembles our universe. Some physicists have proposed that vacuum decay might explain why we do not observe signs of advanced civilizations elsewhere in the universe. The Fermi paradox asks why, given the billions of potentially habitable planets in the galaxy, we see no evidence of extraterrestrial intelligence. Perhaps advanced civilizations inevitably discover technologies that risk triggering vacuum decay. Perhaps most of them are destroyed when an experiment goes wrong, leaving only young civilizations like ours that have not yet reached the danger threshold. This hypothesis is speculative and likely wrong. The energies required to trigger vacuum decay probably far exceed anything achievable by civilizations limited to planetary or even stellar-scale energy resources. But it illustrates the existential weight of vacuum metastability. If our universe is metastable, all civilizations exist under a sword of Damocles. The vacuum could decay at any moment, through natural quantum fluctuation or artificial triggering, erasing everything instantly and irreversibly. Alternative theories propose that vacuum decay might not be instantaneous. If the bubble wall expands slower than light speed due to interactions with matter and fields, there might be time for signals to outrun the wall. Civilizations inside the bubble might have minutes or hours of warning as they detect changes in physical laws approaching from all directions. But this changes nothing. You cannot escape a sphere that expands in all directions simultaneously. There is nowhere to run. You cannot build a ship fast enough to outrace the bubble wall. You cannot shield yourself from changes in the fundamental constants of physics. Warning would only give you time to comprehend your impending annihilation, not to prevent it. The vacuum decay scenario reveals a disturbing truth about the universe. The laws of physics we observe might not be fundamental. They might be contingent, dependent on the particular vacuum state we happen to inhabit. In a different vacuum state, with the quantum fields configured differently, the laws would be different. Particles would have different masses. Forces would have different strengths. Chemistry would follow different rules. This means the universe is more fragile than we thought. It is not built on bedrock. It is built on sand, on a metastable configuration that happens to be stable enough to persist for billions of years, but could in principle collapse at any moment. We exist in a bubble of apparent stability floating in a vast space of possible physics, most of which cannot support our existence. The anthropic principle offers cold comfort. Of course we find ourselves in a vacuum state compatible with life. If we were in a true vacuum state where stable atoms cannot form, we would not exist to wonder about it. We necessarily observe a universe that allows observers. But this observation does not make us safe. It just explains why we are here now. It says nothing about whether we will be here tomorrow. Vacuum decay is the ultimate deadline, not a physical object approaching through space, but a reconfiguration of space itself that could begin at any moment anywhere in the universe. It is the cosmic kill switch, the mechanism by which the universe could erase itself completely and replace itself with something alien and hostile to everything we know. Every second that passes without vacuum decay is evidence that the probability is low, but not evidence that it is zero. The universe has existed for 13.8 billion years without vacuum decay. This suggests the vacuum is reasonably stable. But statistics of one, a single universe observed for a finite time, cannot tell us with certainty whether decay will occur in the next second or the next 10 to the power of 100 years. We live in a universe that might be fundamentally unstable. The ground beneath our feet, the atoms in our bodies, the space between stars, all exist in a configuration that is possibly temporary. Physics itself might be temporary. The laws we discover, the constants we measure, the particles we catalog, might all be artifacts of a particular phase of the universe that will someday end. This is knowledge we cannot use. We cannot prevent vacuum decay. We cannot escape it. We can only wait and hope that the calculations are wrong. That the vacuum is more stable than theory suggests, that quantum tunneling probabilities remain negligibly small for the entire future history of the universe. Some theorists propose that vacuum decay might have already occurred somewhere in the universe, billions of light years away. The bubble could be expanding toward us right now, still millions or billions of years from reaching the Milky Way. We would have no way to detect it until the moment it arrived. The light from galaxies being consumed by the bubble would be redshifted and diluted by cosmic expansion, making the event invisible to our telescopes. In this scenario, the universe is slowly dying, being converted from false vacuum to true vacuum in an expanding sphere that will eventually consume everything. Our observable universe might be one of the last remaining pockets of false vacuum, a temporary refuge that will persist only until the bubble wall arrives and erases us along with everything else. Or the bubble might form tomorrow in a quantum fluctuation in the empty space near Alpha Centauri. 4 years later, it would reach Earth. We would see Alpha Centauri and then Proxima Centauri disappear, winking out of existence as the stars and their planets are converted to exotic matter. We would have 4 years to contemplate our fate. 4 years to watch as star after star vanishes from the night sky. 4 years to know with certainty that we are about to die and that nothing can save us. And then the bubble wall would arrive. The laws of physics would change, matter would dissolve, consciousness would end, and 8 minutes later the sun would follow us into oblivion. This is the final threat on our list. Not a star or a black hole or a cosmic explosion. A failure of the universe itself. A collapse of the foundation on which all matter and energy and structure depends. Vacuum decay is not just death. It is the end of the possibility of existence. The universe does not guarantee safety. It does not promise stability. It offers only probabilities, and those probabilities, while extremely low, are never quite zero. We exist in a cosmos that could erase itself at any moment through no fault of ours, through no action or decision or mistake, simply because the quantum fields pervading all of space happen to be in a metastable state, and quantum mechanics allows transitions between states. This is the price of existence in a quantum universe. Nothing is permanent, nothing is certain. Even the laws of physics themselves are contingent, subject to change through processes we cannot control or predict. We are not standing on solid ground. We are floating on a sea of quantum fluctuations, hoping the waves do not rise high enough to capsize us. The vacuum of space is not empty. It is filled with fields and energy and the potential for catastrophic phase transitions. And every second that we continue to exist, every moment that atoms remain stable and forces operate according to familiar laws, is evidence that the universe has not yet decided to rewrite itself. But the universe is not obligated to preserve us. We are accidents, temporary patterns in the quantum fields that will dissipate when the fields reconfigure. And that reconfiguration could happen now, or now, or now. Every moment that passes without vacuum decay is a gift we did not earn and cannot keep. We exist at the mercy of quantum probabilities, hoping that the improbable remains improbable and that the universe's kill switch remains inactive for just a little while longer. This is the final deadliest object in space, not an object at all, a possibility. The possibility that reality itself is temporary, and that we are living in borrowed time inside a universe that could evaporate like morning fog the instant the quantum fields find their true ground state. The stars continue to shine. The planets continue their orbits. The atoms in your body remain stable. But none of this is guaranteed to last beyond this moment. Welcome to the universe. It wants to erase you. And someday, possibly today, possibly in 10 to the power of 100 years, it will succeed. 6 threats. 6 mechanisms of annihilation scattered throughout the cosmos. Magnetars that can sterilize planets from thousands of light years away. Gamma-ray bursts that sweep extinction beams across the galaxy. Rogue black holes that wander invisible through the dark. Hypervelocity stars that could disrupt our solar system with their gravitational flybys. Kilonovae that forge elements through violence that dwarfs supernova explosions. And vacuum decay, the universe's self-destruct mechanism, waiting in the quantum structure of reality itself. These are not distant theoretical possibilities. They are real phenomena that have been observed, measured, and cataloged. They exist in our galaxy, in our cosmic neighborhood, operating according to physical laws that guarantee they will continue producing catastrophic events throughout the universe's future. We orbit through this minefield, completely exposed. We have no shields against magnetar flares traveling at light speed. We cannot detect rogue black holes until they perturb nearby objects. We see hypervelocity stars only after they are launched. We observe kilonovae from safe distances but cannot predict when the next nearby event will occur. And vacuum decay requires no warning because it propagates at light speed. Space is not the final frontier. It is the killing field. The universe is not our friend. It is not our enemy. It is indifferent, operating according to laws that permit the existence of life only in the narrow margins between catastrophes. The sky above you looks peaceful. The stars shine steadily. The darkness appears benign. But that darkness hides predators that operate on scales you cannot comprehend, with mechanisms you cannot escape, waiting for random chance to align them with Earth. This is reality. Not the sanitized version presented in popular astronomy, where the universe is a wonder to explore and space is the cradle of humanity's destiny. This is the universe as it actually exists. Violent, deadly, and completely indifferent to whether you live or die. If you found this examination of cosmic threats enlightening, subscribe to Cosmic Chronicles for more explorations of the universe's darkest mechanisms. Like this video if you appreciate confronting reality without comforting delusions. Share it with anyone who still believes space is safe. The universe is not waiting for you to be ready. It does not care if you understand the threats or prepare for them. It will continue producing magnetar flares and gamma-ray bursts and colliding neutron stars regardless of whether humanity survives to witness them. You exist in a brief moment of stability between catastrophes. Treasure it, because space is hunting, and eventually, inevitably, space wins.